Hey everyone, so I wanted to start this video by talking on neutralization reactions. We've talked about salts a lot throughout the semester, but we've never really talked about how do we get salts. So sodium chloride, for example, typical table salt, is a product of hydrochloric acid and sodium hydroxide. An acid and a base together will form salt and water. So that's how you would get regular table salt. Here, I'm showing you a similar reaction, except we're getting a different salt. We're getting potassium chloride. But if you notice, what are we reacting to get this salt? We're reacting hydrochloric acid plus a base, which is potassium hydroxide. So whenever you have an acid and a base reacting together, the general products will be a salt plus water. As you can see here, the HCl and the KOH react to yield potassium chloride and water. We break everything up into their respective ions, like we talked about with precipitation reactions, but the same thing happens here, except there's no precipitate, and we cancel out whatever's the same on both sides of the equation. So the chlorine will cancel out as well as the potassium ion will cancel out. And what you're left with is basically H plus OH, which is a proton plus a hydroxide, and that equals water. So this is a very common type of reaction that you will need to be able to recognize. This is called acid-base neutralization. So whenever you get an acid and a base together, you get salt and water. Certain salts, like those that contain carbonate ions, bicarbonate ions, or sulfites, or even sulfides, will react with acids to form gaseous products, for example, carbon dioxide. Here I'm showing you hydrochloric acid reacting with sodium carbonate to form a salt plus carbonic acid. Now that carbonic acid will break up even further to form the carbon dioxide. So that's a two-step reaction. But the main thing here is that when you have an acid and a certain type of basic salt, so those that contain bicarbonates, carbonates, sulfites, or sulfides, will react to form a salt plus water and carbon dioxide gas. So these reactions will lead to gas formation, namely carbon dioxide. You need to become familiar with acid-base neutralization reactions and those acid-base reactions that lead to gas formation. There are some examples of similar reactions on page 132. They describe the reactions between the carbonates, the bicarbonate sulfites, and sulfide salts, and acid plus acid. Next topic we're going to start discussing are redox reactions, which involve reduction and oxidation. But before we do that, I wanted to introduce to you oxidation number. Oxidation number is the charge an atom would have in a molecule or an ionic compound if the electrons were completely transferred. We've already actually gone over a lot of this, and you should know how to do these already. There's only a couple of rules. Well, there's more than a couple. There's 7 rules, but we know a lot of them already because we've learned how to find the charges on atoms before. For us to do redox reactions, we have to know these rules. So let's start going over them. Number 1, free elements. So any element that's uncombined, basically any element by itself, would have an oxidation number of 0. So for example, if I had any free element in a reaction and I had to find its oxidation number, you would put it as 0. Anything that's uncombined. Number 2, monoatomic ions. So ions that are by themselves, or one ion, the oxidation number will equal the charge on the ion. So it's not really anything you have to memorize. It's pretty simple. So if you have something in your reaction that is Fe, iron 3+, well, guess what? The oxidation number will be 3+. Number 3 is something that we've never seen before. The oxidation number of oxygen is usually -2. We know that. But in certain instances, for example, when you have peroxides or superoxides, the oxidation number of oxygen will be -1. Oxidation numbers are basically what we talked about in class when we were setting everything up to a math equation. This is basically the same thing. So what charge does that atom or ion take in that particular molecule? All right, let's move on to the next rules. Rule number 4 states that the charge on hydrogen will usually be +1. We know that. Only exception is when hydrogen is bonded to a metal in a binary compound. So what does that mean? When hydrogen is bonded to just one metal. Binary compound means just two things. So for example, lithium hydroxide, the charge on the hydrogen, if I was to ask you what's the charge on that hydrogen, it would be -1 because the metal takes the positive charge. And remember, they have to cancel out. This is an ionic compound. So you would set it up to 0, and the only thing you would have to remember is that yes, hydrogen is always usually +1, except when it's bonded to a metal in a binary compound. So that's an important one because I like to test you on that one. Number 5, group 1A metals are always +1, and the charge on group 2 metals are always +2. These are the alkaline and the alkaline earth metals. We know that. And fluorine is always -1. So this is simple as well because fluorine sits in the 7th row, and we know that the charge on a fluorine should always be -1. All right, number 6 is actually a simple one as well because we've talked about it in class. This is setting up the math problem, basically. So the sum of the oxidation numbers of all the atoms in a molecule or an ion is equal to the charge on the molecule or an ion. So for example, I've told you that if you have an ionic compound, everything must equal to 0 because ions only come together in one way. If we have a polyatomic ion, we did an example in class, I believe, where it was the carbonate ion, and so it's CO3 2-, and I asked you, okay, so what would you equal this math equation to? We had to put it to -2 because the charge on the entire polyatomic ion was -2. So that's basically what number 6 is saying. The sum of the oxidation numbers of all the atoms in the molecule or the ion are equal to the charge of that molecule or ion. Alright, so the last one is oxidation numbers do not have to be integers. It is one of the last rules, and I rarely test you on this, but you need to know it regardless. So the oxidation number of oxygen in the superoxide ion, for example, would be -1/2. So you have to keep that in mind, that oxidation numbers don't have to be whole integers. This is figure 4.11 in your book, and it shows you the oxidation number of all the different elements. And as you can see, some elements, like nitrogen, have many oxidation numbers that it could obtain, depending on what it is bonded to. Some elements only can obtain one oxidation number. For example, look at the alkali metals, lithium, sodium, potassium. They all are +1, and all the alkaline earth metals are +2. Of course, hydrogen is different. That's not an alkali metal, and we talked about when it would be -1. +1 usually, but -1 when it's bonded to a metal in a binary compound. What I suggest you do is not memorize this, but realize how to get these numbers, and all we have to do is set everything up like a math problem to get the oxidation numbers of these elements. Let's do this example so you guys can get accustomed to how these problems work. Assign oxidation numbers to all elements in the following. So the first element is lithium oxide. This is an ionic compound, so what I would do is I would set it up to 0. I know that oxygen is usually -2. That's the usual oxidation number of oxygen. So I would set it up to 0, and I have 1 oxygen, so that means that it would be -2, and then plus 2x, because I don't know the charge on a lithium. You should know the charge, but let's say I don't know the charge, so it would be 2x. And then you just solve for x. And you can see that when you solve for it, it equals +1. So each lithium has a +1 charge, or a +1 oxidation. And that's simple because we know that lithium is an alkali metal. It sits in the first column, so it will always have a +1 charge. And oxygen we should know too, because it's usually -2, unless it's in a peroxide or a superoxide ion. Alright, so how about the second one, magnesium? Well, that is one of the rules. If you have an uncombined element, then the oxidation number will always be 0. If, for example, the thing said magnesium 2+, right? If I gave it to you as magnesium 2+, then the oxidation of magnesium 2+ would be the charge that it has, 2+. But here, there's no charge on it, so it's uncombined, it's by itself, that means it's 0. How about the third one? So this is what I was talking about. So whenever you have a polyatomic ion, you have to equal the math problem to the charge on that entire ion. So this is a dichromate ion, but the whole polyatomic ion has a charge of -2. So I would equal my math equation to -2. I don't know what the charge on a chromium, but I do know what the usual charge on an oxygen is, but I have 7 of them. So I would do 7 times -2 and then plus 2x, because I don't know what my chromium is, but I do know that I have 2 of them, so I have to put 2x. So then all I do is just solve for x, and that ends up being x is equal to plus 6. And if you go back to your table or figure that we talked about and you look at under chromium, you will see that plus 6 is one of the possible oxidation states that it can obtain. That's how simple this is. We've done this over and over, so this should not be hard. We need to know how to do this if we are going to do redox reactions, which that's what we're going to talk about right now. Alright, so whereas acid-base reactions can be characterized by the transfer of a proton, these type of reactions, oxidation reduction or redox reactions, can be characterized by the transfer of an electron. I have this thing that I use to try to remember what component is getting oxidized and what component is getting reduced. I call it Leo the lion goes grr, right? That's what lions do, right? Grr. Anyway, Leo the lion goes grr. Loss of electrons equals oxidation. Gain of electrons equals reduction. So Leo the lion goes grr. You should use this or any other thing that might help you remember, decide which component in a reaction gets oxidized or reduced. Here I'm showing you an example of a typical redox reaction. It reads, solid zinc reacts with aqueous copper sulfate to yield aqueous zinc sulfate plus solid copper. In these type of problems, you're going to be required to figure out which element is being oxidized and which one is being reduced, as well as figuring out which one is the reducing agent and which one is the oxidizing agent. The way to do these problems is you have to figure out what are the oxidation numbers for everybody on the left side and then figure out what their oxidation numbers are on the right side. So we start with zinc. Zinc solid is uncombined. It's an uncombined element. That was one of the rules of the oxidation number. So that means that the oxidation number of zinc by itself must be 0. Then we go to copper sulfate. Sulfate has a 2- charge. So that means that to cancel out with the copper, copper must have a 2+ charge. So that is the oxidation number of copper on the left-hand side. So now we figure out what are their oxidation numbers on the right-hand side. Zinc is with a sulfate, so it must be a +2 charge because SO4 is 2-, and for it to cancel out, it must be 2+. So zinc ends up being a 2+ charge on the right. So now let's take a look at that. We started with zinc with a 0 oxidation state, and it has changed to a +2. So that means that zinc has lost 2 electrons. If you go from 0 and go to +2, that means that you're getting less negative. So you have lost 2 electrons. Remember Leo the lion goes grr? Loss of electrons means that you're being oxidized. Now let's take a look at the copper. The copper on the right-hand side has an oxidation number of 0. It's uncombined and by itself. So that means that copper went from +2 to 0. That means it is getting less positive. Less positive means a gain of electrons. Leo the lion goes grr. Gain of electrons means reduction. So that means that copper is being reduced. Another thing you have to realize is that since zinc was the one that's being oxidized, it is the one who's actually doing the reducing. So it is said to be the reducing agent. It's always the opposite. So copper, since it was the guy that was reduced, is the component that's doing the oxidizing. So it is the oxidizing agent. So they're always the opposite. This is the basic format to do these problems. All you have to figure out is the oxidation numbers of everybody, and then figure out which one is being oxidized and which one is being reduced. Also notice that sulfate stays the same. Sulfate oxidation on the left is -2 and sulfate oxidation on the right is -2. So that one doesn't get reduced or oxidized. Alright, so I'm going to try to finish chapter 4 in the next video. See you all later.